Yeah, so my name is Tarik. I work with Freddie. I'm in the Department of Ocean Engineering at Texas A&M, and I'll be presenting something called partially averaged Navier-Stokes and how we implemented to PyFR and some initial results for it. So partially averaged Navier-Stokes, or PANS as we call it, it's a variable resolution turbulence model. And the idea for it is if you consider time averaging to be a filter along time, if RANS is supposed to be the closure model for fully average, so infinite filter width, what would be the closure model for partially average statistics? So what would be the closure for a finite filter width? And the idea for that is it really lets you bridge between any level of resolution. So DNS being 0 filter to RANS being infinite filter. And kind of a side benefit of that is you can actually cast many different approaches into PANS. So DNS would be just turning PANS off, same with implicit LES, but you can add in explicit LES, DES, DDES, like unsteady RANS. Really, there's many approaches that you can just cast to the PANS framework. So if you implement PANS, you can have kind of all these approaches. And the idea of PANS is try to model the effects of just the kinetic energy, or really the turbulence that you're not resolving. So in general, it's usually the kinetic energy and dissipation. And you kind of account for that with usually an eddy viscosity-like term. And the idea of it is it's not supposed to be kind of this perfect model that'll let you run millions of Reynolds number simulations. It's kind of just to let you run coarser LES with the same results. You never really get rid of the wall resolve problem. You still have to be wall resolved. But the idea is you can run quite a bit higher aspect ratio cells. You have much higher growth rates in the grid, coarser grids away from the boundaries. So you can get, in terms of degrees of freedom, quite a large decrease with pretty much the same results. So this is kind of the most common way of approaching PANS is to take something like a RANS-like kind of transport terms and modify them to be for any level of resolution. And the idea is that this should hold for any level of resolution. So it should hold for DNS, it should hold for RANS. And the idea for this is you have these parameters and called FK and F omega for this term, or it can be F epsilon depending on what approach you take. The idea is these parameters control how much of the kinetic energy and how much of the dissipation you're not resolving. So it's the ratio of the unresolved to the total terms. And ideally, you would know these terms exactly at every point of space and time, and then your turbulence model would work perfectly, but it's not an ideal world. So these are kind of parameters that you have to set, and they depend on the grid. So these terms can vary from 0 to 1. If you set it to 0 for both, that's DNS. You're essentially turning the PANS off. If you set it to 1, you're fully unsteady RANS. And the idea is actually to just kind of toss in a bit of RANS in some points in space and time to kind of try to up the accuracy a bit. You generally turn it on very little. The levels of this are generally less than 0.5. If you get too high, you're just unsteady RANS and the results aren't that great. So although these are 2 parameters, generally in practice, actually just 1 parameter. The idea being is dissipation. When you take LES, you really don't resolve any of the dissipation scales. Only at DNS are you actually resolving dissipation scales. So your F epsilon would be, your dissipation would be 1. So, and just by the relation of what omega is to epsilon k, you have a fixed value for F omega. So you kind of just have a 1 parameter model, FK, which it's never great to have parameters, but we'll show how the parameters affect some results, and then later on we'll show some how we can just figure out the parameter on its own. So to implement this into PyFR, really any finite element method, definitely not as straightforward as it would be in finite volume methods. One thing being physical constraints. So you have to make sure that your kinetic energy and your dissipation are positive. The reason being, well, one, physically, dimensionally, they have to be positive. But if either term are negative, then you have negative eddy viscosity, and then you have anti-diffusion and your code blows up. So making sure things are positive, not a straightforward and finite element. One thing, or kind of a trick that people who do DG RANDs do is for the mega term, instead of solving for a mega, you solve for the log of a mega. And then when you use it in your eddy viscosity, you take the exponent of it to recover a mega. And this guarantees that the term is strictly positive. Now K has to be strictly positive as well, but you can't do the log term because K is 0 at the wall. So, and we can't have log of 0. So the way we kind of approach the K term is it's kind of a hack to do it, but the idea is if K ever goes negative, you add a source term on the right-hand side, which kind of just pushes it right back towards the lower limit of what K should be. Now, the computational cost of doing this actually varies. It can be it's usually more expensive, but it can be cheaper in some certain scenarios. So for immediately, you have 2 extra transport equations. So there's a 40% increase right there. And in some rare scenarios, you could have a time step restriction because of the eddy viscosity can increase your diffusive CFL. In practice, however, that never really happens. The idea being eddy viscosity goes to 0 at the wall, and that's usually where your finest cells are. So usually not a problem. It can, however, sometimes even help you. The idea is when you look at high Reynolds number cases, especially if you're under-resolved, you need some sort of anti-aliasing. And the eddy viscosity kind of does that for you. It's kind of something similar to a spectrally vanishing viscosity. So one case we kind of looked at is the NACA 0021 deep stall case that takes a lot of anti-aliasing, something like P9 to be stable, whereas you don't need any sort of anti-aliasing with the PANS model. So the case we're kind of using for a benchmark is this cylinder at a Reynolds number 3900. It's a pretty canonical test case. You have it's actually quite complex. It's quite a bit more complex than higher Reynolds number flows for the cylinder. The reason being is you have this laminar separation, and then you have this free shear layer which transitions, and then you have turbulent wake. And the idea is if you don't really resolve any of the kind of intermediary steps before you get to the wake, you have quite different results. So it's a great test case for any sort of model. The other benefit is there's a lot of literature for this case. We're going to be comparing DNS actually from the PyFR group and some experimental results, and both experiment and LES from Parnado. And we take a very under-resolved grid. So the idea is just chuck a highly under-resolved grid and try to compare what PANS would do just to pure Navier-Stokes. So I called Navier here UR-LES, so under-resolved LES. And we want to compare what the FK parameter does to the simulation and how can we somehow figure out what FK should be on its own. And the grid we're looking at is something like 2.5 million degrees of freedom. So I think that's on the order of 6 to 8 times less than what the DNS and LES would be. And it's quite resolved very close to the wall, but then grows really quickly. And that's kind of the approach we want to take with PANS in higher order. So here we have some mean statistics. The left-hand side would be the centerline velocity with the DNS being in the black dots. And on the right-hand side, we have the streamwise velocity contours. So the experiment's at the top, and I kind of added this red line to note where the edge of the recirculation region is. So these red highlights indicate 0 velocity. So pretty quickly off in the left-hand side, you can see under-resolved LES performs quite poorly. The recirculation region is vastly under-predicted. When you add the PANS models, depending on the FK, well, pretty much all the results look better than under-resolved LES, but there's this FK parameter of 0.1 for this case, where it matches very closely to DNS. And here you see kind of the same thing. FK 0.1 matches really closely with the experiment as well. Now, when you look at kind of the velocity profiles at certain X locations, they actually look better with varying FK. So here, the under-resolved LES performs quite poorly. So here on the top, we have the streamwise velocity. The bottom row is the normal velocity. And this is at 3 different X locations. So under-resolved LES quite poor prediction of what the velocity profiles look like, especially in the wall normal direction here. The FK.1 parameter, which seemed to work well in the previous slide, also pretty much exactly matches the DNS here. You see there's just a slight bit of deviation here, but in general, the pans, any sort of FK in this range, which we don't really go outside this range. I don't think anyone really does FK over 0.5. It improves the results. And that's kind of the idea. It's not really, we're not trying to get perfect results. We're just trying to see, can you get something that's better than, for cases that you can't actually do resolved LES, can you get something that's a better prediction than just doing under-resolved LES? When you look at the second order statistics, so the top one would be streamized variance, and the bottom row being the stream and normal velocity covariance, you actually have less variation in the second order statistics when you change FK than you do in the first order statistics. So the optimal FK was really somewhere between 0.1 and 0.2, depending on the location. So like right here, yeah, some 0.2 was pretty good. Yeah, it's kind of the gist between all the points. Under-resolved LES kind of very poorly predicted, not even kind of the rough behavior, it was pretty poorly predicted. The PANS model works kind of well in most cases. I mean, you get the behavior quite well. Sometimes the magnitudes are quite off. But in general, it's a pretty good prediction. I didn't show the normal velocity variance profiles. Those are it wouldn't be quite interesting. Under-resolved LES does it poorly. Pretty much, it was quite easy for PANS to predict a normal velocity variance. So all the different FKs work quite well. So these are results with a free parameter that you have to tune, and no one really likes to tune parameters. So the idea is, can we take this kind of this approach and let the solver just figure out what the optimal FK is? And this method is called adaptive PANS. And the way to do that, you need to be able to quantify really how much turbulent kinetic energy you have locally and what can you resolve. So like, what's the ratio? And the way you do that is you need the physical length scales of a problem versus the length scale that your grid can resolve. Now, one approach that was proposed by Girmaggi and Abdelhamid, so Girmaggi is the man who invented PANS, is to use the turbulence variables to calculate an unresolved length scale. So here you have square root of k over omega. This b star, beta star is not it's not a tunable constant. It's a relation between epsilon and omega. So the idea is you have this unresolved turbulent length scale, LU, and then if you compare it to delta, which would be like either your average grid size or your per element, or like the minimum spacing in X, Y, and Z, you can compare those two, take the ratio, and FK is some function of that. So this seems like there's a constant C PANS here. So it seems like you kind of took one constant and transformed it to another free parameter problem. But generally, it's not a tunable constant. There's actually kind of a physical meaning to what C PANS should be. And the idea is for LES, the guidelines are kind of, for resolved LES, you're resolving something like 90% of the turbulent kinetic energy. So that 0.1 kind of comes from the 10% that you're not resolving. So the formulation I showed is assuming that FK is a constant. And this is not a bad assumption. And if you want to add temporal or spatial variation FK, you can do that without changing the formulation, as long as the variation FK is much slower and much larger than the turbulent length scales and time scales. This is a good assumption. If it wasn't a good assumption, if your FK varied that quickly, your code will blow up almost instantly. So, however, if you want to be really nitty gritty, there are terms you can add into the formulation, the physical terms, not model terms, that account for the fact that FK changes. This is related towards turbulent kinetic energy conservation between 2 points. So there's this adaptive PANS method that came out. It's kind of really for finite volume methods. And the idea we were having is, can we kind of take the benefits that we get out of higher order methods, can you leverage that to help you figure out FK in a different way? And the benefits you get with higher order elements is you have this structured representation of the solution within elements. And with that, you can turn into a modal representation of the solution. And the idea is, if you have, for example, if one's not familiar with it, if you have like a nodal representation here, the solution is the black one. It'd be, for example, Lagrange interpolating polynomials where they each interpolate one of these points. The modal representation is, for example, Legendre modes. You have essentially pretty much frequencies corresponding to different variations in the solution. Now, the benefit of this modal representation is if you actually take out the mean mode, which is this L0, which in this case not very interesting because it's 0, but if you take out the mean mode, all the other modes, the non-zero modes, correspond to fluctuations within the element. So if you integrate these, the square of them actually, you get a good representation of the fluctuations that you're resolving. So if you take, for example, the velocity magnitude and we integrate the fluctuations, we get a good representation of the turbulent kinetic energy that we can resolve. And here P-tot is the total odor term to account for the fact that we have 3D elements. So with this resolved kinetic energy approximation, we can calculate an FK. It's not the same formula as in the previous slide. The idea is now that we have some idea of what we're resolving, we can actually calculate something called a numerical Kolmogorov scale. It's in a perfect turbulence model, this Kolmogorov scale, this scale and the LU from the previous slide would be the same, but if you never really have a perfect turbulence model. So now that because we have this estimate of what the resolved scales are, we can have a better approximation of what FK is. So here we show the what the FK field is instantaneously at a T of 100. So the Girarmagi's method's on top, this is the modal method on the bottom. And when you look at the far field, they're not too different, but what I want you to focus on is actually this region right behind the cylinder. So right behind the cylinder, you have a laminar separation region and you have no fluctuation. So if your FK prediction method was accurate, you should have 0 FK or near 0 FK right behind the wall, which in the modal method you do get, which is makes sense. I mean, the resolved kinetic energy would be 0. And here you actually, with the Girarmagi's method, you don't actually get a good representation of this laminar separation region. So the differences are slight, but you'd expect that to actually make quite a big difference because the results farther on the wake are very dependent on how accurately you resolve the physics near the wall. So the FK we take is constant within elements. This is for the modal method is required because the modes have support over the entire element. For Girarmagi's method, it's not required, but we set it to constant as the average of the cell just for consistency between two approaches. And there's several ways you can implement this. So if you, especially for transient problems, statistically transient problems, you can do on-the-fly adaptive FK, where you calculate FK at each time step, or stuff that are for cases which are statistically steady, you can actually average the FK and over time and just use that, and that actually works quite well. So 2 ways to do it: you can actually just run the simulation beforehand, get the FK, or you can during your startup phases start averaging FK at some point and then freeze it and then just run with that for a while. Both of those approaches work fine. When you use time average FK, you generally are a bit more stable. You have less fluctuations, so you can probably run a bit higher time steps. But in general, neither approach is really terrible. So when you look at the results for the adaptive method, so G representing Girarmagi's method, M representing the modal method, the idea is it doesn't have to be perfect. It doesn't even have to be better than a constant FK case that you tune. You just want something that's good enough. So the Girarmagi method got somewhat close to the DNS results. The modal method got very close to DNS results, pretty spot on with the FK of 0.1 case. And same results you see really with the velocity contours, the recirculation region, the length of it is pretty spot on. When you look at the velocity profiles at certain locations, this is the same kind of results you get from the previous slide, but the modal method is actually better. Excuse me. was actually better in certain scenarios than the constant FK case that we tuned. So the modal method was actually pretty spot on with the DNS everywhere. In some cases, even hard to see here because it's exactly over the DNS. But both methods are able to kind of converge towards these optimal FK values, and the modal method does it marginally better. Now, for the second order statistics, the results, the two different methods are somewhat, in some cases one's better, some cases the other is better. They're generally generally better than the constant FK case in most scenarios, but in other scenarios, the constant FK case does predict it a bit better. But the idea is just not to get perfect results, just something close enough to what an optimal FK case would be. So like if you just spent enough time just tuning the FK constant for a constant case, then you would get better results than any adaptive method. But the idea is, can you just have a fire and forget way of approaching this problem? So in conclusion, we implemented a 2-equation PANS model. So it's the K omega SST model. The results that we used for the case we used for benchmarking was this cylinder Reynolds number 3900. We showed if we use a fixed FK, how these parameters change the results. It doesn't really, there are optimal FKs, but any FK that you choose is an improvement over just under-resolved LES. And with FK 0.1, we're actually pretty good agreement with the DNS in the experiment. And the results I didn't show, just to not clutter the graphs anymore, is PANS has been ran on this case before with finite volume methods, and they were running with something like 2.5 times the degrees of freedom we were, and you get better results with a higher order with half as many degrees of freedom than you do with finite volume. So there's actually a benefit of doing PANS in higher order. And something we tried to do was, can we leverage this higher order representation of the solution within elements to figure out what the optimal FK is. And there were some improvements in accuracy over the current adaptive FK methods that work for finite volume flows, finite volume solvers. And kind of in general, the future work of this is to go towards high Reynolds number flows that aren't not even possible by current LES standards, see how well they compare to experiments. And with that, I'll take any questions.